fogies. I've been using Keck since the very beginning, so for 30 years, and it's such a pleasure to have been part of this Keck community and such an amazing thing to be seeing 30 years of science, part of which will be discussed here, obviously not all of it. But I wanted to also take a moment to welcome you all to Berkeley, the host of this 30-year anniversary of Keck. Hope you'll have a chance to stop by Campbell Hall, although it's a pretty packed schedule. And then I just want to, pay a tribute to our very own Jerry Nelson, who was the inspiration behind the Keck telescopes. He invented the segmented mirror design, which was viewed with great suspicion by many throughout the astronomical community, but he persisted and he won, and now others are basically emulating what he did. So what is it? Imitation is the greatest form of flattery, right? And I'm proud to have had him as my colleague on the Berkeley faculty from 1981 to 1994, and then he moved to Santa Cruz. So Jerry, it's your genius and inspiration and persistence that made all this possible. And of course, so many other people as well, but Jerry was the singular person who really got this going. So a tip of the hat to our colleague, Jerry Nelson. Okay, I have 27 minutes to cover 30 years in the study of the expansion of the universe, during which time it has actually expanded a little bit. So here's the scale factor as a function of time for the usual classical universes that we had been taught about in elementary astronomy classes. And various people had said, well, we've measured the matter density of the universe, and it's roughly 30% of the critical density. So this is how the universe has been behaving, and this is what its future holds for us. But of course, one can test this hypothesis by looking back into the past. So let's look at the beginnings of this diagram here. Here we are at time equals now, redshift 0, of course. Let's choose some arbitrary redshift 1 and ask ourselves, what would be the look-back time at a given redshift, depending on which cosmological model you adopt? So for a closed universe, the look-back time, and hence the distance, is relatively short. In a medium critical density universe, the look-back time is longer. In a low-density universe, the look-back time is even longer. And in an empty universe, which we are definitely not in because we exist, the distance would be the greatest. And so the idea is, choose some redshift for a galaxy, observe it, observe the redshift, figure out its distance, and hence look-back time independently. Do that for a bunch of redshifts, 0.5, 1.1, 1.2, and you will get the observer's version of this diagram. At low redshifts, of course, you just get the Hubble-Lemaitre law, but at larger redshifts, you see deviations from that. And as advertised in a dense universe, for a given redshift, the look-back time is the shortest, all right? So go out and get the redshifts of a bunch of galaxies and figure out their distances independently, independent of the redshift. Cepheid variables and the usual measures of distance don't work at such high redshifts, so you need something a lot more luminous. A supernova fits the bill. In particular, a type 1a supernova, distinguished by the absence of hydrogen, but the presence of this deep silicon line here, as opposed to the type 2, the massive star core collapse supernovae. Those are very luminous, a couple of billion solar luminosities, and they're reasonably standard. And that's because they occur when a white dwarf approaches the Chandrasekhar limit, either by mass accretion from a companion star or through a merging process with another white dwarf. However, they aren't exactly standard. They are known to have different luminosities, as you can tell by looking at type 1a supernovae in nearby galaxies whose distances are known. But Mark Phillips in 1993 noticed that the intrinsically more luminous ones have a slower decline rate than the intrinsically less luminous ones. And subsequently, it was measured that the same is the case for the rise rate. So if you can measure the light curve shape And especially if you do it through different filters, so you can do a correction for dust, then using this multicolor light curve shape method, you can greatly improve, that is, decrease the dispersion in the Hubble diagram. Here's what you get for low redshift type 1a supernovae if you assume that they are perfectly standard candles. And here's what you get after you apply this multicolor light curve shape correction. A decrease in the dispersion by a factor of 3. So this is what makes type 1a supernovae such wonderful cosmological distance indicators. So we measured a whole bunch of them in nearby galaxies whose distances are known through Cepheids or red supergiants or whatever. And now then the idea was to go and find them in distant galaxies whose redshifts you've measured. Okay, so around 1990 or so, two teams formed to do this study, one led by Saul Perlmutter at Berkeley, and he was specifically at Lawrence Berkeley National Lab at the time, and that team actually started first, Supernova Cosmology Project, and then a team led by Brian Schmidt, the high redshift supernova search team formed. And, you know, we weren't always at each other's throats, a little bit like Andrea's talk last night. Having two teams is a good, healthy thing. Each wants to be first, each wants to be best. So if one team is not taking into account some subtlety and the other team is, then that first team looks bad by comparison. It accelerates the progress of the work, pun intended, and especially if you have a bizarre result in the end, having two teams greatly increases the credibility of the result. Other people then take it more seriously. On the two teams, Adam Rees, my postdoctoral scholar at the time, he was an independent Miller Fellow here at Berkeley, but I was his mentor. He was the first on the high Z team to really understand what the data were trying to tell us. And I believe Gerson Goldhaber on the Supernova Cosmology Project was the first to understand what the data were trying to tell them. Both teams used telescopes mostly at CTIO with wide-angle cameras that could take pictures of rather large swaths of the sky, roughly the size of the full moon, thousands of galaxies. Repeat the process 3 weeks later. Some of those galaxies will have produced a type 1a supernova, which you can find through digital subtraction. Okay, so there's the candidate cleverly placed in the middle of that circle. So then my job on both teams, and I was the only person who at one time or another had been a member of both teams. I switched from Saul's team to Brian's team largely for cultural reasons. It was just a different way of doing science. But my job was to get spectra with the Keck telescopes, to confirm that these objects were type 1a supernovae, and to get the redshifts of the galaxies, okay? And so here is an actual photograph from the early days, mid-1990s. There's a very young Adam Rees, and there I am. And I've forgotten which assistant this is. Does anyone remember who that is of the Keck staff? Yeah, maybe Terry in his younger years, but maybe figure it out, Shelley. Okay, so with LRES, the workhorse, still for 30 years. I know it's not on the schedule very much anymore, but I still like it. And Chuck and others who are working on revamping it, go for it. I still really like it. But here's a supernova at redshift 0.5 or so compared with a redshift 0 supernova, and here's the calcium H and K lines, and here's a line of neutral silicon and stuff like that, and a bunch of iron and stuff. So, this was a clear type 1a supernova, all right? So the Keck spectra were absolutely crucial to determine whether the supernova candidates were supernovae of type 1a and to get the redshifts of the galaxies, okay? Absolutely crucial. And here's one IAU circular published by the High Z team, which was actually started by both Brian Schmidt and Nick Sunseth, but Brian became the de facto boss. But you can see all the Ks here are Keck measurements, and I think I counted up 10 of these 15 or so required Keck. And the same was even more true, I think, for the Supernova Cosmology Project, for which I got the spectra, because Keck was really the only telescope, big telescope, to which they had access. I mean, they might have had a few spectra from a few other telescopes, but this just shows the critical role that Keck played in this work. So here are 3 spectroscopically verified type 1a supernovae. and they're dutifully marked with arrows, and they look really faint, fainter than expected. So where would they fall on this observer's version? You know, which of these curves do they fall on? Do they fall on the omega matter of 0.3 curve? No, they fell up there, none of the above in the multiple choice exams that I give in my introductory astronomy class, right? This is not what people expected. Omega matter greater than 1, 1.30. So does this mean omega matter is less than 0? Do we not exist, you know? Or are we dominated elsewhere by negative stuff? Well, no. I mean, you know, in 1917, Einstein had this idea to give a static, or an apparently static universe of the cosmological constant. And though he later renounced the idea in 1929 or 30, when Hubble discovered that the universe isn't static after all, that doesn't mean the idea is necessarily wrong, okay? And so this is what we focused in on. Not omega matter less than 0, but perhaps lambda greater than 0. And here are the actual plots from the early papers. It wasn't a big effect. It was around 2.5 sigma or so. Here's the high Z data. There were fewer supernovae, but I would say the measurements of them were better. We had several filters with which we could do a dust correction. Perlmutter et al. had more objects, but no dust correction. And so these things were, you know, I don't know, 0.2, quarter of a magnitude fainter than expected in a low-density universe, and even fainter than expected in an Einstein-de Sitter universe, which hardly anyone except for the inflationary theorists believed in at the time. Okay, so yeah, the high Z data are fainter than expected. And so then this is the plot that came out in the omega lambda versus omega matter plot. Yeah, you know, some of the contours do intersect omega lambda 0, but most of the area is above that. And so, you know, at some point, even though the results aren't certain, you kind of got to be a bulldog, as my mentor here when I was a Miller Fellow, High Spinrad, used to say. So I was actually privileged to announce this result at a meeting on dark matter at UCLA, organized by David Klein. Astronomers see a cosmic anti-gravity force at work. So reporters ask us, can we use this stuff, whatever it is, to levitate over Bay Area or LA traffic jams? And the answer is no. But the effect is sort of like an anti-gravitating force. And so then the papers were submitted and published. The High Z team submitted in March of 1998, published in September of 1998, and the Supernova Cosmology Project submitted in June of 1999, submitted in September of 1998 or somewhere, December of 98, published in June of 99. And, you know, neither team was absolutely certain at the time, but there was this evidence. Because there were two teams, people took it seriously and tried to figure out where we had gone wrong, and we tried to figure it out as well. But by December of 98, no one had found any obvious thing wrong in anything that we had done. And so this became, you know, the top breakthrough of the year in that year. Okay, so there were other measurements, nevertheless, that strongly suggested that omega matter was of order 0.3, plus or minus 0.1, SDSS, and so forth. And then yet other measurements that indicated that the overall geometry of the universe was flat. In particular, you can see by eye even here that the fluctuations in the CMB, as measured by Boomerang and Maxima, agreed with a flat universe, not with a positively curved or negatively curved universe. So if you take the supernova contours, which were roughly here at the time, and I was told by the organizers to do a historical sort of progression on this topic. Here are the supernova contours. Here's large-scale structure, which to a first approximation is independent of lambda. And then here's the Boomerang result, and they kind of intersect up here. And the concordance model then is omega matter of 0.3, omega lambda of 0.7. So omega total is 1, as had been insisted upon by Alan Guth and other inflationary theorists. And so in Garnovich's paper and others, well, now moving forward to Rees et al., our contours were getting better and better at this point. By 2004, even at the 3 sigma level, you're far away from intersecting lambda equals 0. So unless there's something weird systematic going on, it really does look like something is amiss in the universe. Just quickly fast forwarding, Now there are many, many more low redshift and intermediate redshift supernovae. The Pantheon sample in 2018, here's now where the contours lie. And then 4 years later, the Pantheon Plus sample just published last year. I mean, look at this. It's just, it's incredible. I mean, this is not your mother's or your grandmother's universe, all right? All right, now going back in time again, probing the era of deceleration. If there is something like lambda going on, then instead of one of these curves that we teach in Astro 1, the curve might look something like this. And so even though the universe has recently, the last 4 or 5 billion years, been accelerating and should continue to do so, at one time, you know, in the first n billion years, roughly 9, the universe should have been decelerating because the matter density would have exceeded the dark energy density, okay? And so you'd expect this curve, to see this curve turning around in the sense that at very large redshifts, the supernovae should look a little bit brighter than expected, okay? And so with the Hubble Space Telescope, Adam Rees had a program where he would find high redshift supernovae, and here they are. And Keck actually did play a role in that as well, all right? And in particular with Alison Coyle, I'm not sure if she's here now, but now a professor at UC San Diego, but she worked with us at Berkeley as a graduate student. And here's one of the really high redshift supernovae, 1999 FV at redshift 1.2. And of course, most of the spectrum got shifted to the infrared. But you can see the calcium line that I had pointed out earlier and the silicon features. So this is almost certainly a 1A. So then here's the Hubble diagram. In 2004, we had 6 of the 7 highest redshift supernovae 1A. And then by 2007, we had even more of them. And so this is really very interesting because at lowish redshifts, 0.4 to 0.7, you see the acceleration. But then at higher redshifts, the universe starts behaving like a de Sitter universe, an omega matter equals 1 universe. And so that is really pretty cool. Okay, so since dark energy seems to be real, what is it? Could it be the cosmological constant? Well, maybe, but that's not in very good quantitative agreement with theoretical expectations of 10 to the 120th power, all right? It's way too small right now, and its density is too close to basically being 50-50 with matter, both visible and dark together. So this, as Steven Weinberg and others said, was a real bone in the throat. So it could be some other form of dark energy, not being a property of empty space itself, but rather some sort of an energy that flows through the universe. There's a subtle difference, right, between that and being a property of space itself. So you can define an equation of state parameter. Pressure over rho c squared is W. For, in general, you can say volume to the minus 1 plus W is the density. For normal non-relativistic matter, W is 0. It's 1/3 for photons because they expand with the universe. It's -1 for lambda because it never changes. And it's not -1 for quintessence, for some weird Aristotelian fifth essence that the dark energy might be. That's the idea. And in general relativity, you get a gravitational acceleration of negative quantity rho c squared plus 3p. Normally you ignore the p, right? But if the pressure is negative and more than, you know, the positive rho c squared, then a negative times a negative is a positive and the universe accelerates. Okay, so I'm doing okay now, but a little bit behind. That's okay. So a team called Essence and also the CFHT Supernova Legacy Survey. I mean, I can only do some of the stuff here in a 27-minute talk, but this is a tortured acronym, but it stands for Equation of State Supernovae Trace Cosmic Expansion. Anyway, we used the Blanco telescope at CTIO to find lots of supernovae. Keck, again, was used to confirm their spectroscopic identification and get the redshifts. And so here's what Essence got. We never did completely finish the analysis of the full survey, but here's part of it in Woodvasey et al. Omega matter of 0.274, W of negative 1.05 plus or minus 0.12. So, consistent with the cosmological constant. And the name of the game for the past 15 to 20 years has been nail down the systematic and statistical error bars of W to try to see how close you get to -1. And then even harder, measure the first derivative to see whether it is or is not 0. And that's even harder. The data are consistent with 0, but with very big error bars. The Supernova Cosmology Project was doing this work as well. They have similar results here, omega of about 0.3, W consistent with -1. So the cosmological constant as a null hypothesis is looking pretty good. Fast forwarding again, just to show you what the state of the art is right now, the Pantheon Plus sample, which includes Ryan Foley's foundation, low redshift thing. This is a thing of beauty. I mean, look at this Hubble diagram. And look at the residuals. I mean, it's just incredible. But anyway, that leads to this diagram of W versus omega matter. And if you include then baryonic acoustic oscillations, you get, again, things that are basically consistent with -1. But of course, we can never show that the value is -1.000000 and the derivative is 0.000. We can only make the error bars smaller. And so there's always a chance that there's some weird dark energy that's not lambda that will end up differing from -1 and 0. But whatever. This is why I think it's really hard to play this game now. Nevertheless, we still play the game. And here's what the universe looks like. And so, by 2011, this was pretty well verified by other techniques and complementary techniques and stuff. And so the discovery was recognized with the Nobel Prize, the first of the 2 Nobel Prizes with which Keck was associated. Obviously, Andrea's was entirely based on Keck data, and here this is not the case. But as I will emphasize for about the 5th time, the Keck data were crucial, okay? And so Keck can claim that this is a Nobel Prize as well. And it went to Perlmutter and Schmidt, the 2 leaders, and Rees, who on the high Z team, and my postdoc was the one who first saw what the data were telling us. And this is 1 year after the passing of Gerson Goldhaber. So anyway, the leaders understood that without the rest of us, it wouldn't have been made, this discovery, so they spent a good fraction of their prize money flying us out to participate in Nobel Week. And as Andrea described in her lovely talk last night, it's an amazing week. Let me not go into it. But there's the high Z team. Here's the Supernova Cosmology Project. I should have been in that photo, but was not in it because we were busy that week, and there was only one time to get together for a celebratory lunch. So the high Z team, with which I was more closely associated, was having its celebratory lunch, and there my wife Noelle revealed the consolation prize to all of us who did not technically win the Nobel Prize. It was this t-shirt, Dark Energy is the New Black. Okay, and then finally, is the dark energy really lambda? Well, it's consistent with the data, but we're still not sure. So let's measure the Hubble constant to check. Now, you might think the Hubble constant is the expansion rate now. Who cares? Other than the age of the universe and other important things like that. The reason you care is that the complementary way to going back in time and measuring these curves very precisely to try to figure out how the universe has been behaving is to measure the slope, the Hubble constant right now, and that corresponds to potentially different futures, okay? So that's how the current value of the Hubble constant plays a role. And so the big surprise, which is no longer a surprise to any of you because you're astronomers, but the current rate of expansion, the current Hubble constant, is higher than expected, and this has led to this Hubble tension. Tension with what? Well, just very briefly, because I'm not a microwave background astronomer and I'm running out of time conveniently, but here's the Planck map of the fluctuations, and you take the power spectrum, and it is a thing of beauty. Who knows whether that's significant or not there, but whatever. Look, it's easily 1.5 sigma or something. But anyway, from the sound horizon, okay, and the angular diameter, you can get a distance basically, the angular diameter distance, all right, and the sound horizon is just early physics of a dense gas. I mean, we think we understand that, right? So that plus the standard model, where 70% of the universe is dark energy of the cosmological constant type, and 30% is gravitating matter, they can predict the current value of the Hubble constant. And they get 67.4 with a, to me, ridiculously small error bar, although we are now approaching that. Previous direct measurements had given 70 to 75, plus or minus 4.7, 4 to 7. Possible conflict, but not at all clear. A lot of overlap there, all right? So a team called SHOES formed, led by Adam Rees, and we've published a whole series of papers over the past 18 years, including the latest one by former Berkeley undergraduate UK Murakami. And the goal was to measure the current value of H naught to plus or minus 1% through direct parallaxes of Milky Way Cepheids, Cepheid calibration of supernova 1a hosts, which is where Keck comes in, and then the supernova 1a Hubble diagram. So the basic idea is simple. Take host galaxies of well-measured type 1a supernovae, get HST images, identify the Cepheid variables, right? Figure out the PL relation for them, but the metallicity does play a role. And the whole nature of the game now is in the size of the error bars, so you have to take into account things that you know of astrophysically. And so what we did with Keck was to measure the metallicities of H2 regions in the host galaxies and make the necessary metallicity correction for the PL relationship. And we did that again with LRES. Some of the work earlier was done with Deimos and stuff. I remember Ryan Shornock and I doing long Deimos exposures during the Leonid meteor storm of 2000 and 2001, when we'd go out into the field there in long 1-hour exposures and look for the meteor storm, and then we'd come back and, you know, fortunately there weren't clouds messing up the guiding and stuff. But anyway, so we did that, and here are metallicity gradients in these galaxies. All right, great. So here's, you know, sort of what things looked like, Hubble constant measurements versus time. Here's the low redshift stuff. There's the high redshift stuff. I have 27 seconds. The numbers haven't changed much over the years, but the error bars keep on getting smaller. And here's our latest sample, 42 supernova hosts. We waited till we had 42 because 42 is the answer to life, the universe, and everything. It's a 3-rung Hubble diagram. Cepheids, LMC and Milky Way Cepheids, the host galaxies of 1As, and then the higher redshift Hubble diagram, and we get 73.04 plus or minus 1.04, and UK has refined that to 73.29 plus or minus 0.9. So we're almost at 1%. Planck is this, 5 sigma, something is amiss, smaller uncertainties than before, and we understand them very well. Age of the universe, by the way, folks, is 12.9 gigayears, not 13.8. And there are many other low redshift techniques that give the same answer with somewhat bigger error bars. So it's not all type 1a supernovae anymore. And Rees just published a paper where JWST images of the Cepheids show that crowding is not a problem. And this is just another thing of beauty where the standard deviation has gone down a huge amount from what the HST measurements were giving you. So anyway, possible explanations. Either early or late results are wrong, probably not. I know general relativity is wrong. Oh man, I don't think so. Non-zero curvature of the universe. We're in a large low density bubble, dark matter behaving weirdly and interacting with light. Who knows? Dark energy becoming stronger, a new very light subatomic particle, or maybe there was an early boost of dark energy that caused recombination to occur at a time different from 380,000 years. And you can see here plots of how much these various things would have to change in order to reconcile the early time and late time measurements. So stay tuned. It's a very interesting thing. Thank you to all associated with Keck. Wouldn't have been possible without you. And I hope there is a minute for questions, I think. So thank you very much.